Hi, Calculus. It's Mrs. Jarosik. I am coming to you with the 6.2 video. Regions Between Curves is the name of the section. And what we're going to be doing today for this video is actually calculating area between two curves. So I want to start us with first, if you haven't printed out your notes for 6.2, go ahead and get yourself the printout, or since there's some pictures in this, it might be easier if you can actually print it out. If you cannot, then just get your notebooks or your paper ready. And I want to start with you actually working on this try this problem without me actually going through it. I will put the answer up, but I want you to take a few minutes, pause your video, and then we'll come back with the answer. It's a basic geometry problem just to kind of get our feet wet with area. Okay, so go ahead and try the circle inscribed in a square problem. Okay, we'll be back in a minute. Okay, and we're back. So I drew myself a picture, first of all, of a square and then a circle inscribed in it. It's easy with the technology that I have. So I divided 64 by 4, so I knew each side was worth 16. My area of the square is 16 squared, which gives me 256. And an area of a circle is pi r squared. So the radius, if the diameter is 16, then the radius is 8, giving me 64 pi. And finally, if you're trying to find the area of the square not covered by the circle, so that would be the green shaded part. And that would simply be a subtraction of the total area of the square minus the area of the circle. So 256 minus 64 pi. So something along those lines is what we're getting at in this section, finding the area of a region. Okay, so we're going to start with a problem that can be done without our calculator using geometry, and or we can use integrals, but we have to break it up because if you notice right away, my picture, there's a red V graph, which is an absolute value, and then there's the blue line. So right off the bat, we don't really take the integral of an absolute value function as a whole. We would split this up. So let's first of all have everybody, again, I'm going to pause. I'm going to have you work this out using geometry, meaning if you notice, there are a bunch of line segments throughout this picture. You could use many options using geometry to find the area of the region between the two curves. And just to be sure we understand what that is, we are talking about this area, right? So why doesn't everyone go ahead, pause, take a minute, and let's just strictly geometry. So what do I have shape-wise? There's a trapezoid in there. There are triangles in there. All sorts of ways we could get the area, right? So let's pause, and I'll give you the hint that it is an integer answer. So everybody take a minute to do that. Okay. Hopefully you were successful and got 6 from this. The way I viewed it was one big trapezoid. If you take the part that's shaded and you draw your two verticals or your bases, one gigantic trapezoid. And then I have to subtract some things. So the trapezoid itself is worth 16, if you will, as far as area is concerned. So 1/2, the base 1 is 2, base 2 is 6. And then my distance, notice how the x-axis is scaled. So we have a height of 4 for the trapezoid, giving us 16 total for the trapezoid. And then the area of the triangle, the one right triangle over here, that's the one I tried to draw in the sense that that's the one I was finding. 1/2 times 3 times 6 gives us 9. And then this area for this triangle is 1. And then it's a matter of taking the entire trapezoid's area and subtracting the parts we don't need. So the parts we don't need are the two triangles. So 16 minus 10 is 6. Okay, so by geometry. Next, without our calculator, if we're going to break this up into integrals, if you will, I will first, let's think through this. So we have, I actually didn't want to use that. Okay, we have the line graph, and I apologize, it's got moved. So it's y equals x plus 3. All right. And then the absolute value is absolute value of 2x. So again, we don't take the integral of an absolute value function in its entirety. We would have to split it up. So this segment right here, if you will, is negative 2x. And then the one on the right side, red, right, that's positive 2x. All right, so we have a couple things that we need to do. So if you think through, and I'm going to use the highlight tool to help me out here. When you think about finding this area, okay, and you just want the shaded region, you have basically the line graph is above, if you will, on top of your absolute value function, whether it be on the negative 2x side or on the positive 2x side. The line is always above it. The way I'm going to look at this is I want to actually do a subtraction, but if you think about finding the area of the line, just the line graph itself all the way to the x-axis, well, it's that trapezoid problem, right? Because you have all of this as well as this, okay? So there needs to be a subtraction. So if we find the line from here to here, we need to subtract the portion of the negative 2x underneath, and we need to subtract the portion of the positive 2x underneath, okay? So what we're going to do is we're going to split this up into two separate problems. Where does the negative 2x break off from the positive 2x? Well, at 0 is where it separates itself. So a way to do this using calculus. So as an x value, I am starting at -1. So my lower bound is -1. And the negative 2x line stops at 0. So this particular integral that I'm going to set up right now goes from -1 to 0. And the area I am going to be finding is, and I'm drawing a little vertical for myself right here because I keep saying that the line graph is above the absolute value graph. It's a top minus bottom idea. The graph that's on top area, I'm subtracting the one that's underneath it, that area away from it, because otherwise we're doubling up. So what I'm going to do is literally set it up as a top minus bottom situation from -1 to 0. So on top is x plus 3, the line x plus 3, minus, and then this part of the absolute value graph is the negative 2x portion. Now, we are going to add that to the remaining area from 0 and to the right up until that's 3. So my next integral setup is from 0 to 3. And again, it hasn't changed in the sense that, and actually what I should do, just for the sake of, I have the ability because technology is great for these reasons. Not the best color choice. How about, nope. Why do I keep choosing blue? Let's use green. I'm still top and bottom. The line is still on top. And the bottom is still the absolute value graph. And the setup is going to look very similar, but remember that This is now the positive portion of the absolute value graph. Okay, so if I take this, and what I should do actually, now that I've got it set up, I'm going to move it so I have space to actually work the problem. Okay. Simplify a little bit. So this would be x, let's do it all in one shot. This is x plus 2x is 3x plus 3 dx. And then from 0 to 3 would be x minus 2x, so that's negative x plus 3 dx. So I've got x squared, 3/2 x squared plus 3x from negative 1 to 0 being added to 3x minus x squared over 2. I like leading with a positive. It's not imperative, but I like it. And now I just got to plug in and evaluate. So I've got 3/2 times 0 squared plus 3 times 0 minus 3/2 times negative 1 squared, 3 times negative 1, plus 3 times 3 minus 3 squared over 2, minus 3 times 0 minus 0 squared over 2. And what I'm going to get here is 0. That is also 0. But I've got this minus sign in front of here, so that's 3/2 times negative 1 squared, is 3/2 plus negative 3, or minus 3. And we're going to add that to, this is 9 minus 9/2. Okay, 3/2 minus 6/2 would give me negative 3/2, opposite of that. And then 9 is 18/2 minus 9 is 9/2. So basically what I have is positive 3/2 plus 9/2, which is 12/2, which is 6. Okay. So we can do this by calculus using a method that I like to call top minus bottom, taking the function that is on top, subtracting what is on the bottom, because then you're taking away the overlapped areas to get your final answer. Would you have to do it in this manner every time? No, the exception to the rule on this one is it's a good thing that the top stays the top and the bottom stays the bottom. Sometimes your top and bottom can switch because if there's curves, if there's all sorts of things, things can change. But with this problem, the reason why we had to set it up in this manner, even though the line graph is always above the absolute value graph, it's mainly because it's an absolute value graph. This portion of it is negative 2x. This portion of it is positive 2x. Therefore, we couldn't combine it into one single integral by hand. All right. One last thing that I'm going to do, I'm going to get a little fancy with the technology, is I'm actually going to show you something in Desmos. Okay, and hopefully this is working well on the video. I am going to go ahead and plug in my single integral, and I'm going to talk through it while I'm actually doing this so that you can see how this works on Desmos, okay? So when you get into your keyboard on Desmos in functions and under miscellaneous, you will find an integral symbol. Now, you should be looking at your picture at the same time that I am doing this because I'm using this strictly to calculate, okay? Our entire graph shaded region goes from -1 to 3. So I'm going to do this all in one shot, like I was doing this in the calculator, -1 to 3. Then I have to type in the function. So top was always the x plus 3 graph, right? And just for good measure, let's make that. And then minus, I need absolute value. The absolute value symbol is right here, right above the capital ABC, that's absolute value function. I can put 2x in, and then to close the absolute value, I click on it again, and then I'm going to close my parentheses. Now, it's not going to calculate anything with you until you say dx with respect to x. Look at that. It gives us our area of 6. Okay. All right. So I'm going to go back. I'm going to go back to all right. So thank you for being patient while I have my little technology switchovers here. Okay. So 2 things that I want you to keep in mind when you're doing a problem, finding area between regions, top minus bottom. The key to top minus bottom as a method would be, number 1, all equations are in y equals form, and your bounds are x values. Now, this will play a role as we move forward in 6.2 and then into 6.3. Those are big issues. And you're thinking to yourself, well, it's not any different than what we've been doing. And that is true. However, when we move on to the next example and in other problems and things you'll see on your AP exam, there are other ways to calculate these where the y equals form might change and the x values as bounds might change. Okay, so let's scroll to the next example. Okay. So of course, I'm going to move right into this one might be done a little bit differently than our last problem. And the reason I say that is because when you look for the area between the 2 functions, right? So let's first of all go ahead and talk about, and I already don't like my wording on the question. That's very bad wording, my fault. And if you're thinking to yourself, what don't you like? I know some of you are already on it. They're not both functions. The green graph is most certainly not a function. So the 2 graphs. Okay, so if I were to start drawing, and I'm going to use my highlighter only so it doesn't stay and I have to erase. If I start to, hopefully you could see that. Let me change its color. Okay. If I start to draw top minus bottom, notice what ends up happening. Top is green, bottom is red. Top is green, bottom is red. Top is green, bottom is red. However, when I'm over here on the left end, top is green, bottom is green. Uh-oh. Top is green, bottom is green. Top minus bottom aren't consistent throughout, where no matter I draw my little vertical symbol for top and bottom, it's not the same throughout. So there has to be another method to this. Possibly, yeah. So let's think horizontally instead. Okay, red on the right, green on the left. Red on the right, green on the left. Red on the right, green on the left. No matter where I am, red on the right, green on the left. We call this right minus left. That's why things are going to change slightly. So now that I've established that, no matter where I draw my little horizontal segment, the red is on the right, the green is on the left. Which means the orientation of the entire picture has changed. So in order to calculate this for our purposes, your equations have to be x equals, and your bounds are y values. Bounds are y values. Okay, so What we're doing now is you're thinking of if we were to actually turn the entire picture and visualize it in the other manner, our x's are y's, our y's are x's. So what we have to do now is treat it that way, and we're going to just set it up using the two major points I just said, and you just do everything else, everything the same. So we're going to be taking the integral with respect to y instead. So right, so everything is with respect to y. All right, so I can set this up in one integral. No absolute value going on here, so I can calculate this without splitting anything up. This can be written as one single integral. So I start with my integral symbol, and I need my y values to be bounds, which means my lowest y value is there. My highest, okay, lowest was right here. That's my lowest y value, highest y value. So I'm going from -1 on y to 3. Okay. Now, I said that all my equations have to be in x equals form. Well, the good news is that's already good, meaning check. This one, however, we need to change to x equals form. So that means if I multiply both sides by 2, 2y equals x. Okay. And remember, it's right minus left. So the one, or the equation that's on the right, is my 2y graph. That's the right side, minus, and now the left side. And notice I set up parentheses because my equation on the left side is a binomial. Okay, so right minus left. So 2y minus y squared plus 3 dy. We just do everything the way we would do it otherwise. So y squared minus y cubed over 3 plus 3y from -1 to 3. So when I plug in 3 squared minus 3 cubed over 3 plus 3 times 3 minus -1 squared minus -1 cubed over 3, 3 times -1. 9 minus this is 27 divided by 3, which is 9 plus 9. It's a lot of 9s, right? +1. This would be -1/3, but then you're taking the opposite, so +1/3 minus 3. All right, so we have 9 minus, this would be 3/3, right? So that's 4/3 minus 9/3, -5/3. Did I do that right? So 3/3 plus 1/3 minus 9/3. So 4/3, I think so. And there we go. We're adding, right? So this would be 27/3 plus 5/3, 32/3. There we go. 10 and 2/3, right? Either one of these would be fine. That is our answer. Now, if you wanted to do the calculator with this, I'm going to save a little bit of time in the video. You don't have to put in y's, you just put in x's, and then you put the bounds in as the same thing. So if you're doing a Math 9, which I had shown in a different video, right, and your integral gets set up, right, and you've got your little D, whatever you're supposed to enter, you're faking the calculator out and you just put in everything as though they are x's. You will still get your 32/3, which 10 and 2/3 would be 10.6 repeating as your answer, right? It's going to give you the decimal form. So you can still check this in the calculator. Okay. All right. Now we're going to practice. area between regions, right? So, or I should say, area between two curves, not necessarily always functions. So in this first question, it's a non-calculator question from an AP exam. You can actually do this one, top minus bottom. I believe right minus left might work as well, but notice how your equations are given to you right here. I certainly wouldn't want to force that to x equals if I didn't have to, right? So we're going to go ahead and I'm going to skip right to this part B, find the area. So keep the video a little bit short, maybe go through part A in class. Okay, so I'm going to go right to part B. All right, so let R be the region in the first quadrant enclosed by the graphs of f of x equals 8x cubed and g of x equals sine pi x, as shown in the figure. So if you're looking at the figure, notice they're not labeled for you, f of x and g of x. You need to determine which one is which. So the sine x graph would be the one that's got that max. Sine pi x would be this one right here, the one on top. Right, that should be sine pi x. And then this one is our 8x cubed. Okay, and then if we think about what I was talking about, top, that's a little too top, bottom, right throughout, no matter where I draw, consistent, one integral only. And the nice thing is, right here, we can confirm 0, 0 is that most left point, because if you think about, don't ever assume, but if you plug in 0 for x here, it is 0. And then sine of 0 is 0. So they share 0, 0. So that is the beginning or the most left bound, if you will. So we're going from 0, and then they give you this intersection point right here, which is nice, to 1/2. Top is my sine function, and I'm going to subtract the bottom function. So that's 8x cubed dx. That is our setup. So it's a good refresher of our trig antiderivatives, right? So when we start to calculate, the antiderivative sign is negative cosine pi x, right? And we're going to divide by pi. So wherever you can divide, or you can put the 1 over pi out front. Minus, now if we add 1, that's a 4, and we divide by 4. 2x to the 4th. We're evaluating from 0 to 1/2. If you want to try and get this on your own, pause this and then come back and check your answer. Minus 2 times 1/4 to the 4. All right, so cosine of pi over 2. That's 0, right? So that whole thing zeroes out. And then 1/2. I don't know why I plugged in 1/4. Well, how did that happen? 1/2 to the 4th power is 1 over 16. So 2 times 1 over 16 is minus 1/8. And then we've got cosine of 0, which is 1. So this is negative 1 over pi, and then minus 0. All right, so what I have is negative 1/8 plus 1 over pi, which is absolutely fine to leave as your answer. And there's our answer. And feel free to calculate using your calculator to check. And then, of course, it's going to give you a decimal approximation. So you need to verify that. Okay. All right, let's go to, this would be another top minus bottom. So let's go to, and then this one's a calculator question specifically. So I guess there's a refresher, sorry. Since this is a number 3 from a calc test, from an AP calc test, it is non-calculator. This is number 4, also non-calculator. So 3, 4, 5, and 6 would be non. This would be a calculator question. Okay. And finally, this one, not necessarily off of a AP exam, but I want to do this one next because to get some more practice, and also not one that does not have an actual picture with it. A lot of times, some of the pictures are not included. So we need to at least practice one of those. Okay. All right. So what I'm going to do, actually, let's do it this way. Okay. Find the area of the region enclosed by the graphs of y equals square root of x and y equals 2 minus x. Okay. So I'm going to try and make a rough sketch. So starting at 0, 0, right? Square root of x, 1, 1 is a point. 2, 3, 4, 4, 2 is a point. So I'm trying to be a little bit deliberate with my picture. Okay, that's square root of x. Okay, y equals 2 minus x. All right, so that's negative x plus 2. All right, so if I draw that one, let's go pink, something pink. Okay, positive 2 is my y-intercept. And I know that at positive 2 on the x-axis would be 0. That's a good, right? It does go through 1, 1 as well. So let's do that, right? And it says it's bounded, if you will, by y equals 0 and enclosed, if you will, by that. So here is a boundary, and then there's the curve, and then there's the curve. So what we're talking about is this area right here. Okay. That's what we're looking for. Okay, well, here's the issue. It's not that you can't use top minus bottom, but right here in this dividing line, top here is the green or the square root graph. Top here is your pink or your 2 minus x graph. So I think right minus left works a lot better. And my equations are pretty simple. My equations are easy enough to change to x equals equations. So I'm going to do that. So if I square both sides, I will have x equals. And this one, it's pretty easy. This becomes x equals 2 minus y. And I can just do a right minus left setup. My lower bound or my lowest y value is 0. My upper bound, my highest y value of the region that is bounded is 1. Always on the right is my the pink line or my 2 minus y graph. And always on the left side is my square root graph. So that's y squared. Okay. So when I take my antiderivative, and evaluate, I get 2 minus a half minus a third, and obviously this all zeroes out. So 2 minus a half, well, I'm going to just make everything 12 sixths minus 3/6 minus 2/6. That's the way my brain works. 9 minus 2 7/6 is my area. Okay. All right. I'm going to do one more, but I'm actually going to have you, let's do the one that's non-calculator. This one. And I'm just going to charge you with figuring out if it's top minus bottom, right minus left, and to pause your video and then come back and see the answer. Okay. Okay. So definitely a top minus bottom problem. The top function being y equals 6. The bottom function being y equals 2 square root of x. So top minus bottom, right? Bounds are x values. So 0 to 9 is are the bounds. And then taking your antiderivatives, just be careful with this one. I rewrote it. And then when you add 1, you get 3 halves. And then when you multiply by 2/3, the 2 times the 2, 4/3, right? Okay, so final answer is 18. So I'm going to allow you to pause a minute and try the 2014 problem, number 2. Set it up, plug it into Desmos or your calculator, and let's come back and see how we did. And just remember, radian mode for trig. Okay. Okay, so a couple of quick points before we leave or end the video. When you are setting something up in a calculator situation, as long as the functions have names like f of x and g of x, when you set up your integral, you can use the names of the functions. You don't have to write everything out because you're letting the calculator do the calculation. That's number one. Also, we had to determine which function was which. So I labeled my picture. They don't look for the labels on the picture, but I had to tell which one was on the top, which was on the bottom. So definitely the cosine graph having the shape to it. Also, this is a positive lead coefficient on your parabola graph. Therefore, it should be facing up, right? So the bottom one is my f of x. Top is my g of x. So it's a g of x minus an f of x situation. And then I just plug into the calculator and go. So the 2 notes about the calculator. Remember, at the very beginning of the year, we talked about this. You can put both of your functions into y1 and y2, and then you can use your alpha, right? So that menu I'm referring to is using your alpha button and the trace button. We'll bring up your y menu in the calculator if you have the new operating system. And you just have to keep track of which one you put in y1 and which one you put in y2. The calculator is awesome, but if you have them in the wrong, not in the wrong place, but if you don't remember which one you made y1 or which one you made y2, I sometimes even do this. So I label it for myself, okay? Which one is which, so you know what order to do your subtraction in, okay? And it might be a good idea in class, right? You know, maybe go over some of this a little bit more detailed in either Desmos or actually using the calculator in class. Maybe a good idea if we have time. Okay. All right. And if not, definitely during review season, which we'll have a lot of time with as well. Okay. Well, that's it for the video. Hopefully it didn't end up lasting too long, but if you have any questions, please feel free to mention them to your teachers when you get to class. But this should hopefully give you a very good basis to just start practicing your area between curves. Okay. Have a great day, everybody.